Okay, I think we can start. So it's a great pleasure to start with Miguel Campiglia from Montevideo, talking about logs of theorems, log translations, and asymptotic Einstein's equations.
Thank you very much, Dario, and yeah, thank you so much for the invitation and this unique opportunity. So so I wanted to tell you about a work with my student Gianni Boschetti and a colleague in Montevideo, Guzman Hernandez Chiflet, who he works in a different field, but we got him involved. He was interested in learning, so hopefully we'll. I mean, it's been great because he really came with fresh mind, uncontaminated, and it was really a nice collaboration. So, so there are many logs in my title and in the plans. So I will. There are different logs that I will describe how they are related. So I will be talking about the laws of graviton theorem but in the context of the classical theory. So people call them classical soft theorem. So it is the same as Sang-Min was talking about yesterday. But I mean, my starting point will be a rewriting of this soft theorem in terms of this log deviation of the trajectories that I will describe first, and then I will explain the relationship between this rewriting of the logs of theorem with log translations, and then if there is time, I will sketch a bit on the third point on this matching at special infinity, but I also didn't want to rush. So I mean, if I do 1 and 2, I'm happy. So let me then start explaining what I mean by these words that are underlined. And I will start with a very general comment. So consider asymptotically flat space-time in some asymptotic Cartesian coordinates. And then we have that the metric as some distance parameter goes to infinity. And here I will be, I mean, so far I want to be very general and agnostic about what this R is. And then we will apply it in specific cases. But for now, it's some distance parameter, and the type of spacetimes I will be looking at are those, well, as we want the metric to approach the flat metric, and then there will be a correction that starts at 1 over the R. In particular, when one works in harmonic gauge, where it's typically used to do these perturbative computations, the metric can be brought into this form, and one of the main points of what I'm talking is that these ideas of log translations are present there, although not explicit, but they are present even in harmonic gauge. And there are two. There are two implications of this form of the metric that I'm interested in. One is that in general, when one computes the Christoffel symbols in this asymptotic Cartesian coordinates, they will be ordered 1 over R squared. So you will get 1 more power of R. And the second thing that I will have with this type of metrics is that in general, this form of the metric is preserved by diffeomorphisms that are of the form that have a leading piece as R goes to infinity, a leading piece that goes like log R, and then there is a constant vector that I will call capital L. So this is a constant vector. And these are what are called log translations. So let me. And that's why I wanted to start general, because you will generically you will always have log translations if you are working in asymptotic Cartesian coordinates with this form. Then you may try to fix them, but that will be a separate. Now, let me start with this first consequence of the first point. So, no, we start playing. So when the fact that these Christoffels are 1 over R squared, when you tell you that when you are going to compute the geodesic equation and look at asymptotic geodesics, they will have, so this is an asymptotic geodesic. And this is S is the affine time of the geodesic and affine parametrization. And I'm looking at the geodesic I'm taking it to infinity. So the first term will be I'm considering asymptotically free geodesics that eventually will be the ones that give us the incoming and outgoing particles in a scattering setting. So the first term of the geodesic is just a straight line, and then because of this Christoffel symbols, you will get this logarithmic deviation that will be encoded in some vector that I will be calling C mu, and this is what I refer to as a log deviation vector. Yeah. Yes. Pardon. Sorry, sorry, I'm not. I will soon give references. I mean, of course, I'm doing some review of some general.
No, just
that can be found in many places.
Perfect. No, just to understand, like, so you are solving Einstein's equation close to spatial infinity?
So far, my discussion is purely kinematical. So far, I haven't put Einstein equations yet.
Okay.
So all these statements are purely kinematical. It's just if you have space-time of this characteristic, then the geodesics will behave like this.
But that asymptotic is like in spatial infinity, right?
No, well, I wanted to be agnostic about that. So this idea, I could think at spatial time or even null infinity if you are in non-radiative coordinates.
Okay. Perfect.
Yeah, but that's why I wanted to be. Yeah.
And this asymptotic deviation of the geodesic, it's like you are solving a massive particle or a massless particle.
So it can be either.
Okay.
And I will just in a minute discuss the key difference between the two. Perfect. Yeah. So so actually you can write this log deviation vector. You can write it. I mean, just you can write it in a simple form as in terms of these Christoffel symbols. So you see, because the Christoffel symbols go like 1 over R squared. Yeah. Sorry. Yes.
Sorry, no, I didn't mean to interrupt.
No.
When you're saying, I'm a little. I mean, if asymptotically Cartesian coordinates are just to be chosen so that the metric is eta plus order 1 over R, there's an awful lot of freedom, not just your log R.
Yeah. Oh, yeah. Okay.
Transformations. But then won't that affect your log R deviation vector?
That's a great question. Yes. So it's further freedom, but somehow there is further freedom, but that further freedom that doesn't affect this guy. So sorry.
Yeah, why won't it affect it? Because it's going to change the R coordinates by log R, and I mean there are big changes to the coordinate.
Okay, so displacement. In general, what I will have besides these log translations, in general, I will have Poincaré and eventually BMS. If I'm so those are the settings I have in mind. So and those, I mean, and under those transformations, but the only that acts non-trivially of is the Lorentz transformations. We have a non-trivial action on this vector, but regular translations will not. And what I'm interested is that the log translation will shift this this vector. And
But I mean, don't you have an awful lot more than BMS that preserve this form of the metric?
well, I mean, but then, I mean, I'm talking about the ones that are that do not decay at infinity, right? I'm looking at diffeomorphisms that I'm interested in these diffeomorphisms that are non-trivial at null infinity. At infinity. So I have Poincaré, eventually super translations, and these log translations. Is that?
Okay,
no,
I mean, the rotations don't decay at infinity.
Yeah, no, I mean, they are there. Poincaré, I'm saying.
Rotations plus log R also behave like rotation.
Rotation plus log R will be another rotated log R. So the full group, if you want, is
Okay.
some.
Anyway, let me let you go on. I wanted to clarify.
Yeah.
That.
Sorry, any other question? Yeah, David.
Just to clarify, the C is supposed to preserve this form of the metric.
Yeah.
So you're not allowing, more overleading things that would change. You're not allowing, say, more overleading transformations that would change the asymptotic fall off. You're requiring. Okay.
Yeah, things that preserve that form, right? So that's why I say that will be Poincaré, this, and maybe some. Yeah. Yes. So. Yeah, so one way to write this log deviation vector is by contracting the Christoffel symbols with the asymptotic Cartesian coordinates. So this allows you to, this kills the 1/r squared term, and then you get a finite limit, and the reason I'm writing it like this is that I want to think of this as a field in space-time that I'm constructing out of the connection, and this is kind of will be a central actor in my talk. This field, and that's why I'm giving this name, and then it has this crucial property that it transforms purely inhomogeneously under this log translations diffeomorphism. Okay. Now it comes the question that Hernan was asking, whether if this were time-like or null. Well, or there could be space-like. I mean, at this stage, I can't specify that. Well, I forgot I could have pulled this up. Yes. So let me discuss briefly two cases then. If the case of time-like, so the case relevant for massive particles, what will happen is that this deviation vector depends on the direction along which you are going to infinity. Yes, so it will depend on the velocity and then in the null case, null v mu. Mu is independent. And in the null case, this I mean, so this is a key difference between the massive or the time-like and null geodesics is that there is a non-trivial dependence on the velocity that I can give an example. But in the null case, this vector is constant. And I mean, this type of difference in behavior of how you approach infinity is completely analogous to what was observed in the early discussion of spatial infinity. So I could, the same will be for space like V mu. There will be I can construct the same objects, and there will be a direction-dependent limit, and that was so this is related to this need to introduce some direction-dependent notions at spatial infinity. For instance, is this related to this? I don't know. This they call it something like this. At spatial infinity, and discussing by Weierstecker and Hans. And on the other hand, the fact that this that in the null case this vector is independent of B, it means that you can remove it by a log translation. And remove it by log translation. And that is exactly what this is what the radiative coordinates do, such as Bondi. And this is also familiar in the perturbative context, where when you do the evaluation in harmonic gauge, you will have a non-trivial C mu that eventually you want to people remove by a log, but in this language by a logarithmic translation, so that they are in radiative coordinates. Yeah.
Sorry, I'm just a little confused with your definition. So you are saying C mu is x nu x rho gamma mu nu?
Yeah.
But x itself has C in it. So is this, sorry.
Itself has, right, but to lead in order, sorry, I'm taking the limit to infinity. So this is order R squared, and the order R squared just comes from the velocities. So maybe this is the same as R squared B mu, maybe that was it later. So only the information of the X here, only the information that matter in the X here is only the leading piece. And then the C is encoded in the Christopher symbol. Yeah.
Thank you.
Sorry?
You cannot remove the C mu of V.
Right, no. So neither at time infinity or spatial infinity you can, yeah, right. And that's why no, you cannot remove it. And that's why, I mean, and that's maybe, I think now I'm ready to go to the laws of theorem after this introduction. So I introduce the log division vector and the log translations. And now let me write the laws of theorem and yeah, so we already had talks on this. So let me just briefly mention that we are looking at well, again, this is a classical logs of theorem. We are looking at the gravitational waveform in Fourier space. So this I already extracted the radiative piece, and this depends on the frequency and prediction on the celestial sphere. And then, sorry, I take the limit to 0, and then I have a first piece, the Weinberg factor, let me call it like this, that goes like 1 over omega, and then a logarithmic term. And then, of course, then there are more logarithmic terms, but here I'm only focusing at the leading logarithmic term. And then here, yeah. So, I mean, I'm following mostly both the first paper of Alok Lada and Ashok Sen, and then the paper of Sahu and Sen. And well, under even the notation, this C is from those papers also. And then so Sang-Min already explained the form of this logarithmic of factors. So I will let me explain it in a way that this describes in an intuitive way that can be found in those references. So the intuitive way is the following. So there are two contributions to this logarithmic factor, and they are both related to this log deviation. So the first one is due to the deviation of the hard particles. So I don't know, maybe I put 1 and 2. So there are two terms. The first one is due to the logarithmic deviation of the hard particles, and the second one is due to the logarithmic deviation of the soft particle. This is also what they refer to as a drag term, because the soft radiation is being dragged by the rest of by the momentum of the other hard particles. So this is the drag, and this is deviation. And then let me write these terms. Sorry. So a nice way to write the first term is to go back and start with the soft expansion at tree level or in higher dimensions. So where there's no log term, so soft expansion at tree level or in B greater than 4. There, what you have is that there's the 1 over omega term, and then there is another omega to the 0 term, omega to the 0, H0 nu. And this is one that was explained in the paper of Cachaso and Strominger. And it's and I forgot to. I will also need to write the first one, but okay. So now we are. Sorry, maybe I didn't say it. I mean, we are of course looking at the waveform in a scattering situation where we have some incoming flux of particles and an outgoing one, and then we are looking at the emitted gravitational wave. And so all these factors are expressed in terms of these incoming and outgoing particles that are participating in this scattering process, classical scattering process. And this subleading term then is a sum over all incoming and outgoing particles. And I will, I also put in the units. Mu. Rho, rho, over the end, where n, the vector n is the null direction associated to the point on the celestial sphere where we are looking at. And so P will be the momentum of the particle. Well, and here we are in conventions where so this is we are depending whether they are outgoing or incoming. We put an extra minus sign to have the nice formula, and then J is the angular momentum. Now, as was explaining, as is explained in these papers, what is nice is that so you start with this formula that that is only for 3 level or for higher dimensions, and you say, okay, let's nevertheless apply to our 4-dimensional case with beyond 3 level. And then when you are going to compute the angular momentum in this case, because of this logarithmic deviation, it will diverge. So you will be doing, when you compute the angular momentum, you will do x mu es. And you want to take s to infinity, and then you do the formula for the angular momentum. And here I'm thinking of I mean, if I'm not if s is not strictly infinity, then the momentum will depend on s, and then we'll go to reach a finite value. And so when you use that expansion, you will get something that diverges. And then what they argue is that, well, if I now regard this as, I mean, do the replacement. If I replace now this log s by log omega minus 1, then you get this. Then you get this first contribution to the logs of theory. So you get like 0 mu. So I will now split these two terms when I substitute there. So if I do this substitution, like naive substitution, I will get a log s. Well, sorry, after this replacement, I will get a log omega minus 1.
Miguel, can you comment on this replacement?
Yeah,
It's a prescription, right?
Yeah,
So
they have the like rigorous proof, but this is a way to get quick to the result. Let's say it's not a proof, of course. They have, but it's what is providing the intuition for. Yeah, but I mean, it's not unreasonable. I mean, it's yeah. Yeah. So now I have. Yeah. So I will have then when I have p mu c nu. So the first term, c will give me the p gets contracted with this n and cancels this guy. So the first term is just p mu c nu, and then the second term is minus p mu c nu. And then times c. Yeah, okay. And of course, I mean, here, I mean, when you solve Einstein equations, what you will get is that c is a function of the other particles. So c will be expressed as a sum of the other particles, and then this single sum really is a double sum. And that's why in the expressions one sees, like the one Sang-Ming was showing, is really one has double sums. But I'm keeping this second sum implicit in what C is. Okay, so this was, so then this, okay, let me write the omega minus 1 like this, with a minus 1. And then this whole thing then is what I call there h mu 1. And now let me complete the h mu 2. And I think and then I can at least tell you what I wanted, one first message I wanted to convey. So So the second contribution, again, it's as I was saying, is given by is due to the logarithmic deviation of the soft particle, and so it can be written in this form. Okay, and I realized I forgot to say one more thing about the C's. Yeah. Yeah, let me write it, and then I will explain what I mean by this. And this H mu minus 1 is the soft, the Weinberg soft factor that I hadn't written before. Okay, so I forgot to mention one thing, which was well, it's a small thing. I say that when I was talking about the difference between massive and massless case, I was saying that in the massive, if I'm in a massive case for time-like particles, for time-like trajectories, this guy depends on the asymptotic velocity. Now I can take the null limit of this vector, so I take b goes to becomes null, and when I take this limit, then this vector goes to a constant, a vector, as I was saying that for null asymptotic trajectories, this vector is constant, and I will call this vector C mu scribe plus. I mean, it's just a name, but of course it's just a name, but it's the limiting deviation vector as I take the time-like geodesic, I take it to be null, and that's the one that appears here. So in the what I'm doing here is really I'm rewriting this what is described in these papers of Alok, Sahu, and Sen, but in this I mean they have explicit this constant vector for them is some explicit vector that is proportional to the total momentum, but I'm keeping it like this to be able to discuss this log invariance. So when you have this now the thing is this term when I now do the sum, then this drag term combines with this one, and I can write it. I can write it as and then I forgot for G. Sorry. Then I have C. So this here I combine this drag term with this piece, and then the second one, this one. Yeah, and now, and then yeah, and then the first observation is that now if I do I mean, if I think that I did this exercise I mean, I could have done this exercise in different log frames. So again, the computation in those papers is in a specific frame associated to the harmonic gauge computation, but I could have done this exercise in different log frames, and I would have gotten Each expression of this deviation vector will have deferred by log translation, but the full the full thing is invariant under. So H mu log, where basically what happens is that the log translation shifts these guys. So I was del C I. As I mentioned at the beginning, and the same shift occurs for this asymptotic. So this first term is because you have the difference, is automatically invariant under log translations, and this second term is invariant due to momentum conservation, because when you hit delta L here, these CIs become a constant vector, and then you end up with the sum over of the momentum of the incoming and outgoing particles. And this rewriting helps understand some cancellations that have been noticed in these papers, which was that there was they noticed that one could rewrite they observed that by rewriting their expressions, there was no contribution individual. There was no contribution for to the formula due to outgoing massless particles. And from this, you see, from the splitting I started with, this is a cancellation that from contribution on the first and second term, and it looks a bit mysterious, this cancellation, but from from when you write it in this way, you see that you can say that you could have done this exercise, for instance, in a log frame where the log deviation vector for outgoing null particles was 0. So if you go up to a frame where this log deviation is 0, then there won't be any drag term. And in addition, the outgoing hard null particles will not contribute to the first term. So what was a cancellation before between two terms in these different log frames is just both contributions are 0. So in that sense, it's explaining this cancellation. Sorry, maybe I went a bit too fast then. Yeah. So maybe I pause here. Because maybe I pause here to see. Well, to see the question.
Just on this point. So I guess the original version of that they noticed was that in principle you have this sum that extends of massive particles and massless particles, and there are in principle some of the contributions that come to the massless particles. Then they rewrote. In fact, one of the paper calls like something rewritten.
Right.
So they rewrote it in such a way that you can drop the massless particle and contributions, but you add a new piece that only depends on the total momentum of the massive particles before and after the starting.
Yes.
So if I get this correctly, you're saying that by performing one of these logarithmic transformations, you can eliminate the contribution to the massless particles and add this new term to an effective term to the drag to the C of the massive particles.
Yes, so, exactly. Yes, okay. Because this basically you are doing these log translations, so you are exactly adding a term to all the particles, right?
And so, and the question: there is only one C Scry plus in this game, or do you need to do more than one?
Yeah, well, that was the whole point. That for null, this is the C associated to outgoing null geodesic.
Yeah, but in principle there are many of them.
There are many, but the point is that this vector is independent of the null direction, so it is the same for all of them. That's at the heart of all this. And that's what I said at the beginning, that's why you can remove this guy, and that's what radiative coordinates are that. They remove this for all null. Yeah.
So in a sense, noticing that there is only one C calligraphic I is easier than doing the rewriting that they did.
Right, yeah.
Otherwise we didn't really gain.
Right.
Sorry, another question.
Yes.
Promise I stop. Just a comment about the 3-level soft, because I think there is a bit of historical terminology. So I guess what you refer to as this H0 mu nu is what you get from the Cacciaso structure,
Yes.
so the omega to the 0 soft theorem for the amplitude, right? At 3 levels.
Yes, yes.
And then
it.
you make a guess. Maybe that's also the right thing for H.
Yes.
And then you call it, I mean, it's natural to call it 3 levels of theorem for the waveform.
Right.
Okay, it just so happens that there are, ways to calculate the waveform from amplitude.
Right.
Okay, if you calculate the 3-level waveform from an amplitude at 3 level, you will already get the one with the log.
Oh yeah,
So
I
in
know.
the
Yeah,
amplitude
yeah.
calculation,
Yeah.
it's just a
Yeah,
terminology remark. So
Yes,
the 3-level amplitude
Yeah, this is confusing.
already has
Yeah,
the log.
yeah, I know. Yeah,
in
yeah, I
that
know, I
sense,
know.
it's not
Yeah.
really a 3.
Yeah, oh,
It's
yeah,
not really
okay.
a loop
Yeah.
from the amplitude calculation.
No, yeah, totally.
So,
yeah. Thank you.
Yeah, to bounce back on the previous comment,
Yeah.
this rewriting of Sousa was just for gravitons, right? Was
No, they
so-
do it for. I mean, those papers are classical gravity. I mean, you can do it both either, but.
No, but yeah. So
Oh.
that's what so I'm wondering.
Because there's a cancellation between. I mean, yeah,
Right.
yeah. Because this, yeah. This, yeah, in
So for
electromagnetism,
you will
it's
see
different.
that this cancellation doesn't occur.
Well, because there's no drag in electromagnetism, because the photons don't feel
Yeah.
that are not charged. So one question that I was trying to get Francisco to pay attention now is that whether there could be analogous thing in Young Mills. I don't know, because in principle there could be a drag term there, but I don't know. I mean, that was a sorry.
I guess it's taken of infrared of collinear divergences, so maybe it's true in gravity, but not in Young Mills. But
Okay,
just a
okay, I
guess.
see. Yeah, no, that's.
So if there are other questions so far,
I mean, yeah, I realize, of course, it was a bit ambitious, the total plan, but I just maybe want to add, yeah, some one comment about this C scribe plus, which is that if you yeah, which is something that was something that connects a bit this type of calculations with something that was known also from the early days of this on the asymptotic spatial infinity, which is. So I was saying that we were saying that to explain this cancellation, we go to a log frame where this C scribe plus vanishes, but you will kill all contributions from outgoing null trajectories, but not from incoming massless particles. And so if you have incoming massless particles, you will have a non-trivial logs of theorem that you cannot get rid of by any log translation. And the reason is that there is like a mismatch between the radiative frames at future and at the past. So this is the last comment. Mismatch. Mismatch. Of log of radiative log frames or of log frames at future past. And this mismatch is encoded in the difference the difference between the log deviation vector of outgoing null trajectories and incoming null trajectories. So this difference is invariant under log translations because it's a difference. And the difference is always given by this total momentum. And this mismatch was is known or can be seen also can be seen at spatial infinity. And this connects, but I will not get much time to talk much about, but that disconnect with my third point of trying to understand the laws of theorem from matching at spatial infinity. So at special infinity in this Astikar-Hansen description or this hyperbolic description, I mean, it is discussed in many places that you have these log translations there, and you can choose your log translation so that your gravitational potentials. So again, maybe I will just briefly recall the Weich-Smith at spatial infinity. So your metric is you have this 1 plus sigma over rho square b rho square plus rho square and you have h d h no plus this hyperbolic part. This trimetric. So when you go to yeah, maybe yeah. So when you go to special infinity in for instance, in this type of hyperbolic coordinates, so that you have this field that is like a gravitational potential at special infinity, sigma, and then what is being discussed in many papers. Well, the last one that explains all this very well is the one by compare way, but also there is also the Kevin and Federico de Capone. And then there was a third author. Sorry. No, sorry. And Prabhu. Sorry, this last part that I put in the abstract if there was time, but I was referring to if I had time, but I didn't have. Yes. So to do so in these papers, they prove this antipodal matching condition of the bonding mass aspect by looking at the evolution equation of this sigma. And to do that, you need to adjust your logarithmic frame so that sigma goes to 0 as let's say as this tau goes to plus infinity. But if you impose this decaying condition at future time, then you will see that you will get a non-zero contribution at the past. And this mismatch again was known also from earlier literature, and is precisely this mismatch. Yeah, what I'm saying is that the fact that you have this mismatch between incoming and outgoing null rays, which is crucial to have a non-trivial contribution from incoming massless particles in this logs of theorem, is something that has been noticed when trying to at special infinity when trying to do the matching, this antipodal matching, and that's something that one can find discussion of in the earlier literature, and especially in these notes of Abayastikar, where he discusses how when you have a non-zero total momentum, then there is a discontinuity at special infinity, and this is a manifestation of this discontinuity. Okay, maybe I stop here.
We have some time for questions, Celine.
I wonder whether you have any comment if you promote the log translation to log super translation?
Oh, yeah, so maybe one comment, because I also had, with Andrea, we're talking about that. So here you see there are no, yes, so there's been recent interesting activity on log super translations. But what is nice is that log super translations really are a version of these log translations, but if you think in terms of function on this as parameterized by function on the sphere, they start in a spherical harmonic decomposition that starts at L equals 2. So the L equal 1 and L equal 0 and L equal 1 log super translations are the log translations, and these are really pure gauge in that story of log super translation, and this is perfectly consistent, because here I really want to think of them as pure gauge. So I don't know that, but I don't know, how to, I don't see the relevance of log super translations on this. I don't see that, but who knows?
I suppose that all of this has a simpler analog in electromagnetism, right?
As we were discussing in electromagnetism, there is no drag term because the photons are not charged. So sorry, exactly. And so there's no such a, here the point was that there was a cancellation between the drag of the soft graviton with the other contribution. So so there's no analog of.
So not even in massless.
Not because the direction of the photon is ignorant about the charge content of the. But on the other hand, there is an analog of log translation in electromagnetism, which is log phase. Log gauge transformations that they have been discussed in several papers. So I don't know. I mean, you do a log R. I mean, you take a gauge parameter that is log R, and then here a constant. And these are log U1 gauge transformation. So as usual, what replace the L equal 0, L equal 1 in gravity, spherical harmonic in gravity, in Maxwell is just the L equal 0, just the constant. So there is an analog of the log translations, but there's no analog of this cancellation.
There is no drag term, but the analog of H1, and still you could discuss the log invariance of that term, right? I guess the invariance was not a cancellation.
Well, no, it was a cancellation between these terms here and terms here.
But this term is
and this, I reshuffle this decomposition and I re-express it. Right. I mean, that was the point, to mix these two, to do a different decomposition. Right.
Yes, regarding this log gauge transformation in the U1 gauge theory, is this something that people have looked into, or is it just an analog of what you're drawing from?
I have to think, but people have discussed it as spatial infinity, but I don't know.
At spatial infinity. Yes.
Kevin maybe knows.
I just want to ask whether you think it has this log U1 gauge symmetry has anything to do with this C mu in QED, because I mean, I don't see how. In the gravity case, it's clear because I mean, it's the trajectory that contains the log, and of course, if you do a diff, you do a shift on the trajectory as well. So you shift.
Right.
I mean, exactly where there is the C mu, but this is not how the log U1 gauge transformation would act. So I don't know. I'm asking whether.
No. I mean, my first answer was that there is no analog. But, and I mean, you are providing a different. I agree with you. Yeah, okay. But who knows? I don't know. Maybe there is something.
Any other questions or comments? Carlo?
Yes.
So I guess the rewriting goes on, right? Also for omega log omega squared.
Yeah, I mean, it looks like, but we haven't really, yeah, but it looks like it will work, right, for the higher order, yeah. But, okay.
Yes,
Okay.
Paolo,
We understand correctly that the log omega you compute is come from one loop diagram?
Well, I don't understand the computation.
What is the power of G that you get?
I don't know. Of course, this is C are order G. This C. When I express them, when I solve Einstein equations, I get an expression of C in terms of that is proportional to G, and then this is order G squared.
Order G. So
yeah, I think the other power of G is hidden in this C here.
Okay. So at the end, probably is one loop diagram.
Yeah. This, yeah. I mean, this paper, yeah. Well, sorry, the paper of Sahu and one loop. Yeah.
Okay, I see no more questions, so we can thank Miguel again.